Hi, I'm Ed Burns. I'm here to talk to you about Jakarta Servlet, a new twist on an old favorite. Here's our agenda for today. I will be giving the first and most interesting information at the beginning. Beyond Servlet 4, the plans for what's next, such as they are. Then I'll talk about how Servlet 4 might fit into contemporary developer contexts, such as microservices architectures. The middle of the presentation, I'll dive into the new features that are in Servlet 4, and I will close with a summary. Some information about myself. I am qualified to give this talk as I was the spec lead, the co-spec lead for Servlet, and also the co-spec lead for JSF. These are two parts of the Jakarta EE8 specification family. I'm a frequent international conference speaker, and I've written 4 enterprise Java related books from McGraw-Hill, including JSF 2.0, the complete reference. Let's talk about current plans, such as they are. Well, unfortunately, it is what it is. The Servlet 4 current plan is just bug fixes only. I would like to report some great progress, though, that the Jakarta team has done with Servlet 4. You can check out these links here. The project homepage and today's release is 403. They've got the Java docs set up there. The project leads are Greg Wilkins and Stuart Douglas. These are 2 leading veterans of many Servlet expert groups in the past, Stuart from Red Hat and Greg Wilkins from WebTide. And many of the great features that we have in Servlet are due to these 2 gentlemen and many other collaborators, but I would like to give a special call out to them for continuing the work going forward. These are the Maven coordinates for the Servlet API. However, we do encourage people to just use the Jakarta EE8 jar. One thing that they're working on is all of the Jakarta specs is trying to transfer over the spec documents from Framemaker into toasciidoc, and this is a big job, actually. One of the things that has taken so long with the Jakarta project since 2017, when we did the big announcement of creating the Eclipse EE for J, is just transitioning all of the stuff over in an IP safe and legally acceptable way. And in the Oracle and Sun days, we had licenses for Framemaker. So all of the spec documents were just written in Frame, because that's how all of our documentation team did the work. And this was, we had these specs that were written before toasciidoc was even invented. So once you write a 300-page thing in Framemaker, it would require some significant economic investment of time to convert that over into this more maintainable format. So Oracle never found it economical to do that, and neither did Sun before. So that is one of the bigger tasks, is converting all that stuff over. But they do have placeholders in place. So if you look at and build the Jakarta EE Servlet project, now you get this nice little PDF that is really just a stub, unfortunately. But it shows that it's there, and it's a matter of time and effort to fill it out with the content from the Framemaker documents when we finally get that. The problem is, of course, you have to have a Framemaker license to read it, and that's something that's not free. So I'm not sure how they're going to deal with that, but that's a significant problem. But it's not a hard problem, just takes time and effort. I did do a little bit of polling of some of the thought leaders on what they thought would be an important next step for the Servlet API in terms of new features. And they uniformly said, you know what, this API is pretty solid, pretty good for what it is and what it does. So Mark Thomas, who is the main guy on Tomcat, said when they ran the TCK against Tomcat, they found some bugs in the TCK that they would like to fix and re-enable those tests. Test exceptions were done, and it's better to have a test suite that exercises lots of things rather than simply, oh, the test doesn't pass, let's just exclude that test. That's the kind of thing you have to do in a resource-constrained environment, but hopefully going forward, we won't have that problem as much. Greg did specifically call out the need to implement the will of the project team with regard to package renaming. And finally, wanting to do some bug fixes and clarifications. For my part, I really would like to see us do the ALPN thing right. I will get into the detail on this, but the long and the short of it is, when we developed Servlet 4, it was a part of Java EE 8, and we were constrained to only depend on Java SE 8 features. Now, this is several years down the road, and we actually have JDK 12 coming out, so we could target ALPN, which was not present in Java SE 8, but has been introduced and is still present in subsequent releases. And we had to do quite a bit of strange class path machinations in the specification to enable that to work. And I'd like to undo that. Let's talk about Contemporize. What I mean by that is bringing it into the present day and looking at how things are in a contemporary context with Servlet. So I'd like to ask the question, how is Servlet relevant in the context of a microservices architecture? In order to ask that question, we have to have a definition of what a microservices architecture is. And to the best of my ability, this is a pretty reasonable definition here. Small, loosely coupled, each of the services are isolated from each other. They're highly internally cohesive. They do just one thing. They can be managed, deployed, and developed independent of others, and each service is responsible for handling its own data. So I'm going to take J2EE servlets and ask, hey, is that an example of an early Java microservices platform? Let's look at each of these concerns in turn. Okay, is it a small, is it possible to write each servlet in the microservices architecture small? Yes, well, there's nothing stopping you from keeping your servlets small, but in practice, it was very easy to allow them to get pretty big, chains of servlets and filters, because it was just such an easy programming model. So I'm going to give that a maybe. Loosely coupled can be composed. Well, filters do compose very well, and the filter chain concept is expressly designed to support composing. So I'm going to give that a yes. Is it possible to write servlets such that they're isolated from each other? That is generally not how people use servlets. An outage in any specific servlet would prevent the entire rest of the call flow from continuing. That's got to be a no. Is it possible to have each servlet be highly internally cohesive? Yes, it is. Generally, servlets are used as controllers or act as filters that act on an HTTP request and either pass it on to some other service or send a response. So I will give that a yes. Can be managed, deployed, and developed independent of others? Yes, the WAR file format has always allowed this. Servlets generally don't have much in the way of data, and this was always handled by other parts of the Java EE monolith. But whatever data a servlet does have, it's generally not shared with other parts of the system. I'll give that a yes. So on the whole, I would say kind of sorta, it is possible for you to look at servlets as a very early Java microservices platform. But I want to take this opportunity to point out one of the defining characteristics of a monolith versus a microservices architecture is how much complexity is in the overall system as a whole. And unfortunately, the complexity has to live somewhere. So in a monolith, the complexity is all present in one big glob of stuff. Whereas in the microservices architecture, complexity is spread out a lot more. So you have to be very careful when you do this monolith decomposition, because if you want to get some gains from it, you have to do the architecture such that it's not just taking the existing complexity and blowing it up all over the place, so it's harder to track. You can achieve the gains of deployment and agility, but you have to have very close attention to managing the complexity and making sure your concerns are, orthogonally partitioned out. All right, I'd like to take a time to mention the power of JCP here, which is very good at incorporating industry trends and maintaining compatibility. So servlets, because they've been around for so long, have adapted and incorporated new features from industry trends and best practices all along. So, the packaging concept of, long before there was Docker containers that would allow a application and its dependencies to be packaged, you could have a WAR file, which would, keep the class, webinf lib and webinf classes. That's how you would package your dependencies. Asynchronous programming, that was not really possible when servlets first came out, but as non-blocking I/O and other kinds of reactive programming models came along, it was possible to do that with Servlet, so we adapted and added those things to Servlet in Servlet 3.1, for example. Dependency injection, that did not exist at the beginning, and the concept of inversion of control and dependency injection came along, and then the JCP adapted and said, hey, let's have JSR 250, and that was dependency basic, the @resource annotation. And it since has expanded, of course, with the context and dependency injection, CDI. And Servlet takes great advantage of that as well. And the most recent example that I'll be talking about in some detail today is the introduction of HTTP2. Servlet being the lower level network API for the Jakarta EE platform is where you would say, hey, there's an HTTP2 requirement, and that's what Servlet 4 brings to the table. Okay, I also would like to talk about another aspect of contemporization, servlets within a contemporary microservices architecture system. So there might be some possible reasons to use Servlet for greenfield development in a microservices style. Let's talk about migration here. Teams might be risk averse to trying the whole new way of doing things in terms of architecture and a whole new set of tools in terms of how to implement that architecture. So if you would like to take a more incremental approach, you could adopt the microservices architecture, but keep the old stack, the servlet way of doing things. So this is a more common case where you have a collection of ears with WARs, and then you separate them into individual WAR files. Then you stand up REST services in front of the WARs, and then eventually you have the REST services absorb the functionalities of the WARs. And once you have this big collection of REST services, then you can pretty much get close to having a full microservices architecture. Let us now go into the new feature review. First thing I want to point out is my colleague Manfred Ream has moved over the Java EE examples into Jakarta EE examples, and there's great examples in there for all of the new features that I'll be talking about here. So if you want to have sample code that shows how to use these things, you can go and get it there and drop it into your projects and modify it and keep going that way. So you already know HTTP is important, but briefly, the idea is to improve perceived browser performance through the use of several of these techniques that I will be talking about in more detail in the next few slides. But let's take a look at the actual first abstract of the HTTP2 RFC, RFC 7540. I believe that it's a great manifestation of the notion that perception is reality, especially with web browsers. So you can see here that we want to have a reduced perception of latency with using header field compression and enabling multiple concurrent exchanges between the browser and the server. So the first aspect of this is the so-called request-response multiplexing. It's a fully bidirectional communication. It lets you do more things with a single TCP connection, and it's enabled by defining some terms. So a connection is basically a TCP socket. A stream is a channel within that connection. A message is a logical message, such as a request or response, and a frame is the smallest unit of communication in HTTP2. So this is how that breaks down. You could have a number of connections open, although in HTTP2 they try to do as much as possible with a single TCP connection. And within that you have a number of streams that can be simultaneously opened and independently prioritized. And each stream can have messages that are flowing back and forth, and a message is made up of individual frames. So this is what the request-response multiplexing looks like. You have your browser on the left and your server on the right here, and both sides of this connection can introduce or initiate content. Generally, of course, the browser starts it out by making a request, but once that stream is established, you can have request and response headers flowing back and forth. The odd numbered headers are reserved for coming from the client to the server, and the even numbered headers are reserved for coming from the server to the client. And once you break down the communication into frames, you're able to interweave the logical streams over a single TCP connection, so you're able to get more throughput that way. This is what the individual specification of the frame looks like in terms of actually bits. You have a 24-bit length, followed by an 8-bit type field, and 8 bits of flags, a single byte or bit of reserved field, and then you have this stream identifier, which is a 31-bit integer, and then the frame payload, the actual data of the frame. For example, in a body frame, that would be the HTML, for example. Now, the type field can be any number of things. We have data indicating actual content that I mentioned, headers, your HTTP request response headers, a priority frame, which indicates how the client is to deal with this or process it with respect to all of the other frames that are coming in. Reset stream is a signal type that says, okay, we're going to close this stream. Settings frame, which enables you to change aspects of the communication back and forth. Push promise is a frame that comes from the server to the client saying, I'm going to promise to be pushing you something. Ping is important to keep the connection open, because if you're going to keep this long-lived TCP connection, you have to keep sending some kind of heartbeat to enable the TCP network routing algorithms to optimize things correctly. Go away is the frame that's sent when the server wants to close connection. Window update and communication are two lower-level networking aspects. I also wanted to mention header compression. So perception is reality, and we were perceived that HTTP was going slower than it needed to because we were spending a lot of time and a lot of network bandwidth sending the same set of headers back and forth all the time. Host, it's always the same thing. User agent, given one browser talking to a server, it's not going to change its user agent during the course of its interaction with the server. So why send them every time? What they decided to do was have the server and the client keep tables of headers, a state machine, and then to send references and updates to the tables. Furthermore, they defined pseudo headers for the most common things. So you wouldn't have to spell them out. These are just actual int numbers, kind of like an enum. Stream prioritization. I mentioned that you have a number of different streams in a connection. So you can have individual priorities for each of these streams. And so that's an additional 40 bytes in the frame which is the stream ID and a wait and an exclusive bit. This is just advisory. There's nothing that says clients must do this or they're invalid HTTP. They could simply not even deal with the prioritization and treat everything the same. It's just that it's possible to achieve and squeeze out more performance if the client and the server both do this correctly. So here are some examples. If we have stream B and stream C, depending on stream A, we have assignment of 4 to stream B and assignment of 12 to stream A. It says, well, we should give a proportionally higher number of resources to processing C than we do to B. Another aspect is you could have this arrangement where we have B, D, and C depending on A with these priorities here, 4, 16, and 12. And let's say we determine, or the server says, you know what, these things that are in stream D should be given higher priority treatment from the client. So you can assign a exclusive bit, which will mean that it is the only thing that depends. So it basically moves it up a level in the hierarchy. So it will be giving all of the treatment before anything from this level that doesn't have the exclusive bit set. All right, we'll talk next about server push. One of the HTTP 1.0 and 1.1 have stood the test of time. There's no question about that. But it has enabled, or it has caused web designers to come up with lots of funny techniques for optimizing their performance. So, for example, browsers would limit the number of TCP connections that could be open to a specific server. So if you had a server that was optimized and just had tons of network connections attached to it, its TCP stack was tweaked so that the max sockets was way up high, what servers would do, what web authors would do, is this thing called domain sharding, which is a way to have several different DNS names that actually point to the same server, so that when you write out your web page, you reference your inline resources, not your inline resources, your dependent resources, using the different DNS names. So the browser thinks, oh, well, I can open up 8 sockets to this guy, and then 8 sockets to that guy, and 8 sockets to this other guy, but they're all the same server, really. That's one trick. Another trick that was done to increase performance was resource inlining. So this is where you have a base 64 encoded image, the bytes of which are actually in the page, rather than having the browser issue a separate request. And this was done because it would allow priority treatment it would allow faster rendering of the page, for example. So with server push, we don't need that because what's going to happen is the server knows what the browser will need before it asks for it. So it just will start giving the browser what it needs before the browser even knows it needs it. And there's no corresponding JavaScript API, but you can combine this thing with a server-sent event to sort of take advantage of it, where the server pushes stuff into the browser's cache that is not going to be in the page, but then then the server uses SSE to tell the browser to go and fetch it. But when the browser goes to fetch it, it'll already be in the cache because we already pushed it there. So that's one little trick that you could do. The most important thing to remember with server push, though, is it does require some rethinking of how you author the page, because the original assumptions that I just put out there, all these workarounds, domain sharding and resource inlining, you would actually get worse performance now in a climate of HTTP2 because there's all this complexity left on the table that you're not taking advantage of if you're still using the old techniques. So how do we get, when the browser is making a connection to the server, how does it determine whether it's appropriate to use HTTP2? Well, the first case is if you're using HTTPS, you don't need to worry about it because the protocol negotiation happens inside of the TLS negotiation. So when opening up the TCP socket and establishing the SSL connection, there is a application layer protocol negotiation technique that will specify a protocol header, not header, but a sort of statement. It's called H2. And when the browser sees H2, we know, aha, we can just go straight to HTTP2. We don't need to do anything else. However, if we're doing not secure, that is H2C, we have to use port 80, and then the server would send a 101 switching protocols to upgrade from HTTP2. So most of what's great about HTTP2 comes for free in using Servlet 4. So all of this binary framing, stream multiplexing, header compression, that's just, you get that for free. It's not exposed in the Servlet API. Push, on the other hand, is exposed. So let's take a look at the specifics of push. In the normal case, the browser will make a request to the server and then get a resource back, and then we'll parse the page and determine that it needs to get these follow-up resources. With server push, we have a bit of a different thing, but it only works with methods that are cacheable and safe. So that is essentially read-only methods that don't have, or methods that don't have a request body. So that's basically get and head. So you can't do push with post, options, or trace. You can do it with get and head. The API that Greg Wilkins suggested, which is what we did put in Servlet 4, has you asking the servlet request for a push builder, and then you can add headers and methods and all the other things, the string that you're pushing, and then you call push. So here's what a flow diagram looks like with that. So the browser calls get on the servlet container, which invokes the servlet service method. And then let's say the servlet service method discovers that the browser will need these new additional resources. In the case of JSF, it's a very easy thing because the servlet knows exactly what is in the page and what all the follow-up resources are, because the page author is forced to tell the system, basically, this is my page, these are the resources that go along with it. So in this case, the servlet will call new push builder and add the style sheet and push it down, and add the script and push it down, and these will come down to the client, and then finally the client gets the page. So it's faster to render. So this is the stock faces servlet that's in JSF 2.3, which is a part of Jakarta EE 8. And the faces servlet service method, which I just showed there, determines if this is a resource request. So there's two different kinds of requests in JSF, standard page requests and resource requests. And the resource request is for handling scripts and images and style sheets. And if we determine that's a resource request, we tell the resource handler to go ahead and handle it. Otherwise, we do the JSF request processing lifecycle. Now, here's what the encode resource URL looks like that was referenced in that handle resource request, which we'll actually ultimately call encode resource URL. This is actually code from the JSF implementation. We obtain the reference URL to the resource, and we push it, and then we encode the response URL there. So this enables JSF users to take advantage of server push without having to rewrite any of their code. So that's kind of handy. Something else that's new in the HTTP2 specification is the way we do trailers. Now, trailers were in HTTP1, but they weren't exposed in any Servlet API until now. So the point of trailer is when the sender desires to send metadata at the end of the message, after the response. So it's basically headers that come after the body. You might ask, why would I want that? Well, that would be useful for message checksum, for example. and digital signatures. So here's what a trailer looks like. You have your, in 1.1, that is. So this is a 200 response. We're saying the content type is text plain. You must say the transfer encoding is chunked, and you specify a header whose name is trailer, and the value of the header is the name of the trailer. So this way the client knows when the data is done, the request is done, that it's supposed to read this trailer called foo. In HTTP2, there is, as I said before, this concept of pseudo headers. You must not put pseudo headers in as trailer values. So that's just a proviso. And some use cases, digital signature, message integrity tech. Also, gRPC makes use of trailers when it runs its transport over HTTP2. gRPC requires HTTP2. So that was another reason why it was important to have Servlet 4 support HTTP2, so we could enable gRPC-based applications to interact with Servlet. This is what the trailer API looks like. So when you're interacting with a Servlet request and you would like to read the trailers, you have to ask, is the trailer field ready? And only when this returns true is it safe to call this get trailer fields map that will return you the trailers that you can read. When you're sending a response, you ask, or you tell the response, here are the trailers. You pass it a supplier, and that allows the implementation to call and get them when they're ready. And if you need to interact with the trailer, so you can deal with the supplier by getting the trailer fields. And the supplier is a JDK Streams Java SE8 interface that was added. So this is what it looks like in a flow diagram. And here is an example of a test servlet that interacts with the trailer feature. So we are doing a post. So in the do post, we are adding a header saying this is transfer encoding chunked. We're adding a header that is trailer with 2 different trailers. And we're saying, okay, set trailer fields, and we're passing this closure that is the map, which is going to be a supplier here. And we're putting the bar 1 and bar 2 trailers in there. And the system will make sure that these are obtained and sent at the right point in time in the request flow. So that's what that looks like right there. Another new feature that we added was mapping discovery. This has nothing to do with HTTP2, but it does allow for some new sort of meta programming that's now possible with Servlet. It allows for the Servlet to discover how it was invoked. Now, it turns out that all of the Servlet implementations already had to do this. You know, they had to implement filter change and Servlet mappings, and to discover which one to invoke on any given request for the path. But that information wasn't exposed to the developer. So we now expose it, and it accounts for all the different various ways for the container to invoke a servlet. So there's quite a few different ways that a servlet can get invoked, it turns out. Request dispatcher forward, request dispatcher include, async context dispatch, get name dispatch. These are all the different ways that servlets can get invoked, or filters. And there's also this required request attribute that is present to indicate different kind of mapping invocation. So we have this API HTTP servlet request get servlet mapping, which returns an immutable servlet mapping. And that immutable servlet mapping has a mapping match enum, and these are the constants here that tell you the different kinds of mapping invocations. And the servlet mapping also includes the match value, the pattern that was used to do the mapping, and the name of the servlet that was invoked. We also did some improvements regarding encoding. The request encoding was to be specified as UTF-8 now, and we provided XML elements for specifying the request character encoding and response character encoding. These were basically ambiguous before Servlet 4, and now we've firmly said, okay, it's UTF-8, and you can explicitly specify it as well. We added some Java SE8 default methods for implementing things to make it a little bit easier to implement servlets. We added a generic filter and an HTTP filter that took advantage of these default methods. And so we'll close with the summary now. Servlet 4 brings HTTP2 to the Java EE platform. It has significant improvements, incremental improvements, and it maintains the backwards compatibility promise for which Java EE is famous. So thank you very much, and I hope you enjoy the rest of the Jakarta EE live stream.